Yesterday we were talking about a bar being fixed. Two bars being fixed together, the other one inside the other one. Being fixed together, 1 and 2. After that, we change the temperature. So today, we are going to look we're having 2 of them today. Also, we have number 1 and we also have number 2. And then we fix here. We also fix here. This one is steel and this one is copper. So now we change the temperature. We change the temperature of the 2. So as we change the temperature, at the end, the change in length will be equal. At the end, the change in length will be equal. But we need to observe what will happen before the change in length becomes equal. So which one is going to stretch more? The copper is going to stretch more. Ne? Which one is going to stretch first? Copper is going to stretch first. Ne? So, as we increase the temperature, copper will start to expand due to temperature. Okay, firstly, I said change in length for steel is equal to change for copper is equal to change in length for steel. So when we change the temperature of the bar, you are saying this one, the copper, will start expanding before this expands, ne? Meaning due to temperature, the copper will start expanding, which will be original length times coefficient of expansion times change in temperature. That's what you are saying, ne? On the other hand, is the steel started to expand? This one has started to expand, eh? Yes. So this one, the steel, it will get shorter because this one is pushing it. So the steel, it will start to get shorter and shorter because it's being pushed by the copper, meaning there is the change in length for the steel. So now, the steel now start to expand due to temperature. It has reached the higher temperature. Start to expand. As it start to expand, it start to push the copper backwards. The steel start to push the what? The copper backwards. Therefore, the copper will reduce the original length due to the pushing of the steel. Do you understand that one? Yes. And that, again the copper, it has pushed the steel maybe to this position. Now the steel is going back. Meaning, due to temperature, the initial change in length you had now is being reduced by the increase of the temperature, which is it will be like this one. Yes. Is in that manner. So in this case, you can take this one this side, and you take this one on this other side. This one is for copper, this one is for steel. So changing the two will have original length for copper change in temperature, plus original length for steel is equals to X for steel plus X for copper. So does this, okay, let me finish there. We have L copper times copper changing temperature, plus L times is equals to F steel L steel over A steel times E steel plus F copper L copper over A copper times E copper. So tell me here, does the length cancel out? Does the length cancel out? The length, it won't cancel out, ne? Why? Can we assume that the length of this one is equal to this one? We can't, because it's a series connection. Ne? Under series connection, we cannot say the length of this one is equal to the length of this one, unless otherwise given as equal. So meaning the length, it will remain like that. The temperature change for this one, is it not the same as the temperature change for this one? It is, ne? So meaning we can take the common factor of temperature change. We're left with LC times this one plus LS times this one is equals to, is FC equals to FS or not? Are they equal or they are not? They're equal, eh? Because where there's a force, there's also reaction. So as this one pushes this one, this pushes back. If ever the force is not equal, for instance, when I push here, the wall is not moving because the wall is exerting the equal reaction. If ever the force was not equal, I will keep on pushing without stop, non-stop. In that case, the force is not equal. But once the force is equal, I cannot able. I will have a point to stop. Same applies as this one. The change in length end up stopping somewhere because at that point the force becomes equal. So therefore, for these two, I can take a common factor of the force, which it will be force LS over LA ES plus LS over AC, EC, close brackets. So when it's connected in parallel this way, unlike the one of yesterday, this is the formula which you should use. There is no need of driving the formula. As long as you know that you will use this formula to calculate your change in length, your total change in length, you will use this one. To calculate your total change in length, you will also either use this one or use this one. And this one is your total change in length. So this one is for the one which will expand more. This one is for the one which it will expand less. When it's connected in series. So you can just check if you do have this formula in your textbook, in your formula sheet, the one given. If you are not, you can just try to understand it. How does it go? Then you use it to calculate the force. I guess here you'll be required to calculate the force. So this one is different from the first one. The only difference is, if you check the first one, this one here and this one, those L's, they cancel out. Then also the sign there on the other one is positive. It's negative instead of positive. That's the difference from the other one. So from there, it means you are covered for both parallel and series when you apply axial force and when you apply a temperature. Is there any question? Or is there any problem from the textbook you will want us to solve? Yes. Exercise? Exercise 2. Page? Page 46.